Now we shall begin with the new chapter, chapter number 9. Okay, what is the rigid body? That is the first concept, and there is a difference between the rigid body and the solid body. That also we shall discuss. Okay, now see, rigid body generally means a hard, solid object having a definite shape and size. A system of particles in which interparticle distance remain invariant. That is very important. Interparticle distances do not change. Then it is called the rigid body. A solid body can be deformed. In the solid body which we are generally having in our day-to-day life, all these bodies are solid body. There is a possibility of deformation. You can change its shape by applying some pressure, by exerting some force, okay? But rigid body cannot be deformed. A rigid body is an ideal concept. Now this is an ideal concept, generally not possible in day-to-day life. Hence it is difficult to obtain in practice. In reality, solid bodies can be stretched, compressed and bent. Okay, in general our day-to-day life, these solid bodies can be stretched, compressed, bent, means it can be deformed. Hence solid bodies are not perfectly the rigid bodies. Okay, rigid body cannot be compressed, cannot be bent. Okay, that is the main difference, or we can say is deformation is not possible. Now we talk about the elasticity. What is plastic body and plasticity? The property of the body by virtue of which it tends to regain its original size and shape when the applied force is removed, then this property is called the elasticity. Means the object comes back to its original position. Okay. So, the property of the body by virtue of which it tends to regain its original size and shape when the applied force is removed is known as elasticity, and the deformation caused is known as elastic deformation. Whatever deformation is caused during the application of the force is known as elastic deformation. Try to understand elastic deformation means if that force is removed, then that deformation will also come back, or the body will come back to its original shape and size. That is the elasticity. That is a property of the body. Now, if we apply force to a lump of putty or mud, they have no gross tendency to regain their previous shape, and they get permanently deformed. Okay, such substances are called the plastic. Okay, and this property is called the plasticity. Once deformation is caused, it does not come back to its original position. Putty and mud are close to ideal plastics. Okay. Now, elastic behavior can be explained with the help of spring ball model. We know that in solid each atom or molecule is surrounded by neighboring atoms or molecules. These are bonded together by interatomic or intermolecular forces and stay in a stable equilibrium position. When a solid is deformed, the atoms or molecules are displaced from their equilibrium positions. Whenever deformation is there, what will happen? The molecule will be displaced from the equilibrium position, okay, which causes change in the interatomic distance. So there will be a change in the interatomic distance. Say for example, if this molecule is experiencing the force, then interatomic distances will be changed. Okay. When the deforming force is removed, the interatomic forces tend to drive them back to their original positions. and the body regains its original shape and size. Try to understand when the force is removed. Okay, force is removed, then what will happen? This body, or rather this atom which was earlier changed, or rather earlier its position was changed, will try to come back to its original position, and that brings the body back to its original shape and size. The restoring mechanism can be visualized by taking a model. This is a model. Try to understand how this molecule comes back to its original position. So this is a kind of model, and this model is of spring ball system, which is shown in this figure. When the balls here, these dark spheres which are shown here, they are representing the atoms, and the spring represent the interatomic force. These springs are showing the interatomic forces. Okay. If you try to displace any atom, if any of this atom is tried to be displaced, okay, if you just pull this in this particular direction, if you apply the force in this direction, you pull it, okay, from its equilibrium position, that atom will come to another position. The spring system tries to restore the ball back to its original position. What does this spring system do? When you apply the force this side, then this spring system will try to bring this sphere to its original place. If you apply the force in this direction, then this spring system will have a restoring force in the opposite direction, and this sphere would come back to its original place. Thus, elastic behavior of the solid can be explained in terms of this microscopic nature of the solid. Okay. Now we shall talk about the stress. Okay, its unit dimensional formula we shall discuss. When forces are applied on a body in such a manner that the body is still in static equilibrium, it is deformed to a small or large extent. Whenever it is in static equilibrium, if the force is applied, then there will be a slight or large deformation. Now, deformation depending upon the nature of the material of the body. This deformation is not same for every material. This deformation is different for different material. It depends on the type of material of the body, the magnitude of the deforming force also. It also depends on the force which you are applying from outside, which is a deforming force. So it depends on two things: material of the body and the magnitude of the deforming force. The deformation may not be noticeable visually in many materials, but it is there when a body is subject to a deforming force. Try to understand. Whenever, say for example, you are applying some force on a solid body which you are having in your hand, okay, sometimes you are pressing the ball pen, okay, then that force is deforming the body, but that deformation is not noticeable. A restoring force is developed in the body, and when you just remove that force, then the body comes back to its original position. Okay, so, and this restoring force, which is bringing the object back to its original position, this restoring force is equal in magnitude, but in the opposite, in the direction of the applied external force. This restoring force, try to understand, this restoring force per unit area is known as stress. If F is the applied force, then the restoring force will also be F only. Try to understand action and reaction. Forces are always in pair. So action force is applied force, that restoring force is the same as that of the applied force. Okay, so this F force is the applied force, and A is the area of the cross section of the body on which the force is applied. then magnitude of stress is force upon area. Okay, force upon area is nothing but stress, and its unit is Newton per meter square, or in the memory of scientist Pascal, it is PA, that is Pascal. Its dimensional formula is m1 L minus 1 T minus 2. Okay. Now we shall talk about the longitudinal stress. Now first of all, try to see this figure. Here one cylinder is shown, or a rod is shown. Okay, its original length is L. Okay. Now force F is applied. Okay, on its cross sectional area here. Okay, then there will be a change in length. Original length is L, and after the application of the force, this length changes by delta L. So final length will become L plus delta L. Okay. Now this restoring force per unit area, when the length is changed, try to understand. The restoring force per unit area, when there is a change in length is there, then it is called the tensile stress. Try to understand. Whenever there is change in length, then it is tensile stress. If this cylinder or a rod is compressed under the action of the applied force, the restoring force per unit area is known as compressive stress. So whenever there is a stretching of the cylinder, okay, the restoring force per unit area is called the tensile stress, and when the cylinder is compressed under the action of the applied force, the restoring force per unit area is known as compressive stress. Okay, so this tensile or compressive stress is denoted by sigma, and in general it is known as longitudinal stress. Okay, because it changes the length, that is why it is a longitudinal stress. Now we talk about the strain. We will discuss the longitudinal strain. If a solid body under external force is, its dimension are changed by three ways. Whenever you have the solid body, its dimension can be changed in different three ways. Either you can change the length, or you can change the volume, or the shape is changed. Okay. The fractional change in the dimension of the body is known as strain. Again, the fractional change in the dimension of the body is called the strain. Now we talk about the longitudinal strain. Now see, the deforming force produces a fractional change in the length, which is known as longitudinal strain. Now say for example, you have length L. Okay, you have the length L, and if the external force is applied, then that length changes and it now becomes L plus delta L. So the change in length is delta L. Now this change in length, that is delta L upon original length. Okay, change in length, that is delta L upon original length, that is defined as the fractional change in length. Okay, and that is called longitudinal strain, which is denoted by epsilon L. Okay, so epsilon L is delta L change in length upon original length. Okay, if the length increases, the corresponding longitudinal strain is a tensile strain. If length increases, okay, then it is called the tensile strain. Okay, if the length decreases, then corresponding strain is called the compressive strain. Okay, if the length reduces, okay, then this is named as compressive strain. Okay. Now we shall talk about the tangential or shearing stress and shearing strain. Now see this figure. Two equal and opposite deforming forces are applied to the cross-sectional area of the cylinder, and there is a relative displacement between the opposite faces of the cylinder. Okay, so here one force is applied in this direction, okay, and the other force is applied tangential to the upper surface. Then what will happen? The lower part is remaining here, the upper part is slightly displaced from its position of equilibrium. Okay, let the displacement is delta x and the theta angle is made. Okay, the restoring force per unit area developed due to the applied tangential force is known as the tangential or shearing stress. This restoring force per unit area which is developed due to the applied tangential force is nothing but tangential or shearing stress. As a result of applied tangential force, there is a relative displacement delta x between the opposite faces of the cylinder, which is shown in this figure. Okay, there is a relative displacement, you can see, by delta x. This goes slightly this way. Okay, if you have a book, okay, say for example you have this book, okay, and you apply the force on its cover this way, then that book will be slightly, or upper part will slightly move this side, okay, and the new position is attained. Say for example this displacement is delta x, and if you take this height as L, then this becomes theta, as slightly it is going away from its original position. Okay, so this is the phenomenon which is explained here also in a different way. Due to this, the strain so produced is known as shearing strain, and it is defined as the ratio of relative displacement of the face to the length of the face or a cylinder. So here, if you consider the displacement, okay, say for example you have a book this way, and the force is applied here as it is shown in this direction, then this corner will come here, or rather if I show it in a different way, okay, if this is applied a force in this direction, this corner will come somewhere here, okay, and this corner will go slightly away. Okay, so here the angle theta is produced, and this displacement is delta x, and the height of this book is L, or cylinder if you have, then this height, okay, this height is L. Okay, due to this, the strain so produced is known as shearing strain. Okay, stress is force per unit area. Okay, because of this, the strain is produced, which is nothing but there is a change in shape. Change in shape is immeasurable quantity. So we are trying to define the shearing strain, and it is defined as the ratio of relative displacement of the face to the length of the cylinder or a book. So relative displacement here is delta x, and the length of the face is L. So shearing strain is delta x upon L, which is nothing but tan theta. You can see from the figure, if this corner is brought somewhere here, then this delta x upon L is nothing but tan theta opposite upon adjacent. Okay, opposite upon adjacent, that is delta x upon L. So tan theta is equivalent to theta, that is delta x upon L, where theta is the angular displacement of the cylinder or a book from its vertical position. This theta is very small, so tan theta is equivalent to theta in radian. Okay, here a body subjected to shearing stress is shown in this figure. You can see this figure. Okay, in this A body is subject to a shearing stress is shown. Force is applied parallel to the surface, and this corner earlier was in this particular direction, but slightly it has been moved. Okay, earlier it was having its position somewhere here, but when the force is applied, this has been moved slightly this side. Okay, earlier this was like this, but slightly it has been moved by an amount delta x. So this delta x upon L, try to understand here, theta is produced. Okay, so delta x upon L is nothing but shearing strain. Okay, thank you very much. Try to see this video, okay, 2-3 times, and try to understand these all new concepts. Okay.